Welcome to the Deep Dive. We're here to sift through complex information and pull out what's really important, what's truly interesting for you. Today, we're diving deep into a pretty significant piece of research, the AlphaEvolve paper. It's from Google DeepMind. Our source today is the white paper itself, detailing the research.
Yeah, and this isn't just, a small update. It feels like a fundamentally different approach for AI, tackling really tough problems in science and engineering. So our mission here for you is to unpack what AlphaEvolve actually is, what it can do, and maybe touch on what it means for, AI and for us going forward.
Okay, AlphaEvolve. Sounds big. So in simple terms, what is it?
Well, the paper calls it an evolutionary coding agent. Basically, think of an AI that can make algorithms better all by itself.
How? By actually changing the code.
Exactly. It's not just fiddling with parameters, it's rewriting the instructions, the code itself.
Okay, wow. And how does it do that? Is it just guessing? Random changes?
No, not random. It's evolutionary. That's the core idea. It starts with a bunch of algorithms, right? And then refines them over generations.
Generations.
Yeah, based on feedback. It uses things called evaluators that automatically check how well each algorithm is doing on a task. It's like constant performance testing for code.
Ah, okay. So it's kind of like natural selection, but digital. The best code survives and gets improved.
That's a really good way to think about it, yeah. And what's exciting, or maybe a bit daunting, is the kind of problems they think it can handle. Big scientific challenges, optimizing huge computer systems.
It sounds incredibly ambitious. I mean, has it actually done anything concrete yet? The paper mentions some early wins.
It has, yeah. Even at this stage, some pretty impressive results. For example, it came up with a better way to schedule tasks in Google's massive data centers.
Okay, data center scheduling. Sounds niche, but I guess at Google scale.
Exactly. Even a small efficiency gain there means, big savings in energy and resources. It's very practical.
Right. Real world impact. What else?
It also found a way to simplify the design for some hardware accelerators. Those are the special chips driving a lot of modern computing.
Simplify them while keeping them working the same.
Yep. Functionally equivalent, just a more efficient design. Think cleaner blueprints. And this is pretty wild. It actually helped speed up the training for the language model that AlphaEvolve itself uses.
Wait, it improved the AI that powers it.
An AI helping build a better version of itself.
Okay, that is interesting. Self-improvement. But the paper also mentioned actual new discoveries in math and computer science.
Yes, exactly. And this is where it gets really groundbreaking, I think. It's found completely new algorithms that are proven correct and actually better than the best ones humans had developed in some really tough areas.
Better than humans. Can you give an example, something specific?
Okay, yeah. The big one they highlight is matrix multiplication, multiplying two 4x4 matrices with complex numbers. AlphaEvolve found a way to do it with just 48 basic multiplications.
48.
Yeah.
What was the previous best?
The previous record holder was Strasson's algorithm from 1969, right? That used 49 multiplications for this specific size.
So one less multiplication.
One less, yes. But it's the first improvement for this exact problem in 56 years. 56. Mathematicians, computer scientists, they've been chipping away at this stuff for decades. And an AI just found a better way.
Wow. Okay, 56 years. That really puts it into perspective. It makes you think about how we usually discover things, right? The paper touches on that too.
It does. It acknowledges, the usual long slog of scientific discovery, ideas, trying things out, backtracking, experiments, validation. It takes ages.
And people have been talking about using LLMs, large language models, to help with parts of that, like brainstorming or designing experiments.
Exactly. There's been excitement there, some success too. But the paper argues that getting entirely new breakthroughs, real discoveries just using LLMs, that's been the tough part.
So AlphaEvolve is positioned as the solution. Right. Or a solution.
Kind of. It tackles that challenge by combining LLMs, which are great at manipulating code and language, with this robust evolutionary computation framework. Generate, test, learn, repeat. Many, many times.
Right. That combination seems key. The evolutionary part grounds the LLM's creativity. So how does it actually work? Can you walk us through the process?
Okay, so first thing, it works best on problems where you can automatically evaluate a potential solution. That scoring is crucial for the feedback loop.
Makes sense. You need to know if it's getting better.
Right. And the things it's trying to discover, new math objects, algorithms, heuristics, they're all represented as algorithms, as code.
And the LLMs generate and fiddle with this code.
Precisely. The LLMs generate new code, critique existing code, suggest modifications. They evolve this whole population of algorithms. But crucially, the system then runs the code and uses the automatic evaluation to see if the suggestions actually work.
So it filters out bad ideas from the LLM, grounded in reality.
Exactly. It prevents the LLM from just hallucinating incorrect solutions. And this whole evolutionary cycle, this feedback loop, lets it discover things that might look very different from where it started. It's not just small tweaks.
Okay. And this is particularly good when finding the algorithm is the goal.
Yes, or when the algorithm describes how to build the thing you want. Now, the paper compares it to an earlier system, Fun Search. You might remember that one.
I do, vaguely.
Yeah.
How is AlphaEvolve different? Better.
It's a pretty big step up. Fun Search worked on short snippets of Python code, maybe 10, 20 lines. AlphaEvolve handles whole code files, hundreds of lines.
Wow, much bigger scale.
Yeah, and it's not just Python, more languages. It can handle longer evaluation times too, using parallel computing. Needs fewer LLM samples, interestingly, but really benefits from the latest, most powerful LLMs.
And the prompts are better.
Much richer prompts, yeah. More context, more feedback packed in. And importantly, it can optimize for multiple goals at once, not just one single score.
Multi-objective. Okay, so way more powerful, more flexible, but limitations. You mentioned the need for automatic evaluation.
That's the main one right now, yes.
Yeah.
If you need a human expert to look at the result or run a complex physical experiment to see if it worked, AlphaEvolve isn't set up for that yet. It needs that clear, automated score.
Got it. Okay, let's get into the components. Figure 2 in the paper lays it out. What's the first step?
It starts with task specification and evaluation. Basically, the user defines the what. What problem are we solving? How do we measure success? That's the evaluation function. Mapping a solution to a score or scores to maximize.
And the user gives it a starting point.
Usually, yeah. An initial solution, even a simple one, and maybe some background info papers, equations, whatever might help.
Okay. Then there's an API.
Right, this is neat. User can just mark off blocks of code in their existing project using special comments, like #evolve block start. AlphaEvolve then focuses on evolving just that block, using the rest of the code as context.
Practical. Makes it easier to integrate. What about how it represents solutions? You said it's flexible.
Yeah, flexibility in abstraction. It's not just about raw code lines. It can evolve, say, a function that builds the solution, or even evolve a search algorithm that then finds the solution. Different problems need different approaches, and this flexibility is key.
Interesting. Evolving the search itself.
Okay.
Next step.
Prompt sampling. This is where the LLMs come in. Because they use state-of-the-art models with huge context windows, they can feed them tons of information. Past good solutions, instructions, maybe bits of literature, even how the results look.
And the prompt itself can evolve.
Yeah, meta-prompt evolution. It tries to figure out how to ask the LLM better questions over time. Very clever.
Okay, so super detailed prompts. Then the LLM does its thing, creative generation.
Exactly. They use an ensemble, Gemini, Flash, and Pro, balancing speed and quality. The LLM digests all that info and suggests changes, often as these diff blocks.
Diff blocks, like code changes.
Yeah, shows exactly what to add or remove.
Right.
Search replace format makes it very concrete. Or for small bits of code, it might just rewrite the whole thing.
Okay, suggestions made, then evaluation. Back to the automatic scoring.
Yep. Run the modified code, get the score using the function the user provided. They have tricks here too, like an evaluation cascade test, promising ideas on harder and harder cases.
Makes sense. Filter out things that only work on easy stuff.
Right. And they can even use an LLM to give feedback on things like code simplicity, which is hard to put a number on, plus lots of parallel evaluation to test many ideas quickly.
And you mentioned optimizing for multiple scores. Why do that if you only care about one thing in the end?
It sounds counterintuitive, maybe, but they found aiming for good performance across several related scores can actually lead to better results on the main target score.
How so?
It encourages more diverse solutions, pushes the system to explore different kinds of trade-offs. You might find a really novel approach that excels overall, which you'd miss if you were too narrowly focused.
Interesting. Keeps the search broad. And all this knowledge, the good solutions, are managed by the evolution component.
Correct. There's an evolutionary database inspired by algorithms like MAP elites and island models. It's all about balancing exploration, trying new things, and exploitation refining the best things found so far. Keeps diversity, prevents getting stuck too early.
Sounds complex.
Okay.
And this all runs on a distributed pipeline. Lots of computers.
Oh yeah. It has to. It's an asynchronous system, a controller managing things, lots of LLM samplers, proposing ideas, tons of evaluation nodes testing them out, all working in parallel for maximum throughput.
Okay, that gives us a really good picture of the machinery inside AlphaEvolve. Let's circle back to those results. We talked matrix multiplication, that 56-year record breaker. What else?
Well, beyond that specific 4x4 complex case, it actually improved on the state-of-the-art for 14 different matrix multiplication tasks. And often, the algorithms it finds use nice exact numbers, integers, half integers, which is great for accuracy.
So it's not just finding weird approximate solutions.
No, often exact and provably correct. And figure 4 in the paper really shows how much it can change the starting program, the optimizer, the initial setup, the loss function. It tinkers with everything.
A deep rewrite.
Totally. And they also mention this idea of humans collaborating with AlphaEvolve, like giving it a good starting idea could boost it even further.
Okay, what about those open mathematical problems? That seems like a different beast entirely.
It really is. And the results are maybe even more striking here. They threw it at over 50 open problems across different fields, analysis, combinatorics, geometry.
50? Wow. How did it do?
It matched the best known human constructions on about 75% of them, which is already impressive, suggesting those human solutions might be optimal.
Right, then.
But on about 20% of the problems, it actually beat the best known results, found new, better constructions.
Beat the state of the art on 20%, starting from simple ideas.
Often, yeah. Simple or random starting points. The method here was usually evolving a search algorithm, a strategy for finding good solutions given a time limit, and maybe the previous best as a target to beat.
And it found complex strategies.
Yes, multi-stage adaptive strategies, things that are pretty hard for humans to design manually. It just evolved them.
Specific examples. Any standouts?
Let's see. In analysis, it tightened bounds on some inequalities, refined a setup for the uncertainty principle. Combinatorics, it found a new upper bound for the Urdu's minimum overlap problem. Geometry.
Yes.
This is cool. It improved the lower bound for the kissing number in 11 dimensions.
Kissing number. How many spheres can touch a central sphere?
Exactly. The previous best was 592. AlphaEvolve found a configuration for 593. Just squeezed one more in. Plus, new results in other packing problems, and they worked with top mathematicians like Terence Tao on some of these.
Incredible. AI is a mathematical research partner. Okay, shifting gears to Google's on infrastructure. Data center scheduling, you said it found a simple but effective heuristic.
Yeah, that's the interesting part. It wasn't some super complex thing, a relatively simple rule, but it outperformed the complex system they were using. Led to that 0.7% recovery of compute resources across the fleet.
Which is huge at their scale. And better than, say, deep reinforcement learning for this.
They argue yes, because the heuristic AlphaEvolve found was easier to understand, debug, predict, and deploy. Critical for infrastructure.
Makes sense. What about Gemini, their big AI model? How did AlphaEvolve help there?
Training these huge models is all about efficiency. They use a system called Palace for writing fast code for their hardware. Optimizing how work is split up, tiling is key.
Usually done by hand or auto-tuners.
Right, takes ages. AlphaEvolve optimized the tiling heuristics for a key part of Gemini, a matrix multiplication kernel. Got a 23% speed up on that kernel, which translated to a 1% cut in Gemini's total training time.
1% of Gemini training time. Still massive savings, I bet.
Oh, absolutely. And it cut the optimization time from potentially months of engineering down to days. Plus, again, it's Gemini optimizing its own training.
That recursive improvement again. What else inside Google? Hardware?
Yeah.
Compilers?
Both. It helped optimize a key arithmetic circuit design for their TPUs, the AI chips. Found a rewrite that cut area and power functionally identical, validated by the TPU team. That was Gemini's first direct contribution to TPU circuits.
Wow.
And it directly optimized compiler output. Specifically, the code generated by their XLA compiler for flash attention, a crucial mechanism in transformers.
Optimizing the compiler's output.
Yeah, got a 32% speed up on that specific kernel, 15% speed up in related processing for a major model. All rigorously checked for correctness, of course.
So really broad impact across software, hardware, algorithms. Okay, the paper mentions ablation studies. What did they learn from taking parts away?
Right, ablations test component importance. They check things like, do we need the evolutionary part? Does the rich prompt context matter? Meta prompts, evolving full files, powerful LLMs.
And the verdict?
Basically, yes to all of the above. Figure 8 shows it pretty clearly. Each piece contributes significantly. It's the whole system working together that delivers the results. Take one piece out, performance drops noticeably.
It's a synergistic effect. The paper also positions this relative to other work, right? How does it fit in?
Yeah, it builds on decades of evolutionary computation, genetic programming, but the big twist is using modern LLMs as the engine for generating variations, for mutation and crossover, essentially.
Automating the creative part of evolution.
Kind of, yeah. It's a big step beyond fun search, as we discussed scale, flexibility, multi-objective, leveraging frontier LLMs better. It also relates to other work using LLMs to guide evolution in robotics or optimization, but AlphaEvolve seems particularly general and powerful.
Are others doing similar things?
There are related efforts, yeah. Some combine LLM evolution with reinforcement learning or concept learning, and there's work like AI Co-Scientist, but that often uses natural language hypotheses, whereas AlphaEvolve uses code, which is directly testable.
So the executable code representation is key.
It seems to be a major advantage for the kinds of problems AlphaEvolve tackles. It really connects the AI's ideas directly to verifiable performance.
Okay, so let's wrap this up, bringing it all together. What are the big takeaways, the implications for AI for us?
Well, I think the research really underscores this, maybe surprising, power you get when you combine top-tier LLMs with automated evaluation in this evolutionary loop. It's unlocked breakthroughs we haven't seen before, both scientifically and practically.
And the flexibility is important too, tackling problems in different ways.
Exactly. Sometimes you evolve the solution directly, sometimes you evolve a function to build the solution, sometimes you evolve the search algorithm. That adaptability seems crucial. You can think of AlphaEvolve as using computation at test time to massively boost the base LLM's ability, guided by machine feedback.
And that could lead to better base models in the future.
Potentially, yeah. They mentioned distilling these gains back into future models, a kind of self-improvement cycle for AI capabilities, and seeing it already improve its own infrastructure, its own LLMs. That's pretty profound.
It does feel like a step change.
It does. The main hurdle still is that reliance on automated evaluators. That limits it in some areas, especially natural sciences, where evaluation is complex or requires physical experiments.
So future work might try to bridge that gap.
That's what they suggest, maybe combining high-level LLM feedback on ideas with the low-level machine feedback on implementation. That could be really powerful.
So to sum it up, AlphaEvolve seems like a major leap. AI not just solving problems, but discovering fundamentally new ways to do things, creating new knowledge.
Absolutely. It shows this potential for autonomous systems to tackle incredibly complex challenges, making real discoveries and tangible improvement.
Okay, that is definitely a lot to think about. So here's something for you, the listener, to ponder. What does it really mean when AI can not only find answers, but fundamentally improve the tools and methods of discovery itself? If AI becomes this active, creative partner in science and engineering, what frontiers might open up that we can't even imagine right now?
It really pushes us to consider the future relationship between human intellect and artificial intelligence and how that partnership might reshape scientific progress and, well, everything else.